Hiroshima Space Center on September 7th last year and has been flying smoothly so far. At around midnight tonight, which will be by then January 20th, just as the date changes here in Japan, the descent operation to the lunar surface will begin, and the lunar landing is scheduled for around 0:20, 20 minutes past midnight. During the broadcast, we'll first provide an overview of the SLIM mission to signify its importance from an engineering standpoint, and take a look at the science that we're hoping to achieve with SLIM. Then the landing operation will be relayed from around midnight, so do stay with us. We're going to start with a history of Japanese lunar exploration and SLIM itself.
ここまでどんな歴史をたどり、その先にどんな未来が広がっているのでしょうか。日本の月探査の幕開けは1990年に打ち上げられた光学実験衛星飛天。月の重力を使って探査機の加速と減速を繰り返す二重スイングバイに世界で初めて成功。日本はアメリカ、ソ連に次いで月の周回軌道に探査機を送り込んだ国となりました。探査機の速度を自由自在に操れるこの技術は宇宙探査の大きな一歩となりました。飛天に続くミッションとして2007年に打ち上げられたのが月周回衛星かぐやです。かぐやには当時史上最多となる15種類もの観測装置を搭載。アポロ計画以来初となる本格的な月の観測が行われました。月の地形や地下の構造を明らかにし、世界の月探査を先導する存在となったのです。かぐやの偉業は科学技術の成果だけにとどまりません。月の地平線から昇る青い地球の映像は多くの人々の心を捉えました。
正直言ってかぐやの印象的な映像を見て、研究者としての人生が大きく変わったと思います。私はもともと地球の磁気圏のプラズマの研究をしていたんですけれども、かぐやの映像を見たことによって、地球のことだけでなくて、月のような他の星の研究もしてみたいという、もう絶対面白いはずだというそういう意識を持ちました。
かぐやの成功をきっかけに国際宇宙ステーションの後に続く国際月探査への機運が高まりました。この動きを受け NASA をはじめ各国の月探査機がかぐやに続いています。かぐやの成果も受け継ぎ、新たに開発された次世代の着陸技術で月への着陸探査を行うのがSLIMプロジェクトです。国際的な月探査であるアルテミス計画に先行して月探査の新しい未来を切り開くことが期待されています。
SLIMではまだ世界で誰も実現したことがない100メーターという高い正確さで狙ったところに降りるための技術の開発をしてきています。これができるようになると、例えばクレーターの隣にあるこの岩石の観察をしたいといったような科学者たちの声にも応えることができるようになります。傾斜地に降りるための技術と合わせて、降りられるところに降りるのではなく、降りたいところに降りるということをこれから実現できるようになるというふうに考えています。
SLIMが着陸するのは三木の海の近くにあるクレーターしおりです。SLIMで採用されたのが斜面でも着陸できる2段階着陸方式。姿勢を傾けながら最初に1本の主脚を設置、その後斜面に倒れ込むようにして残りの足を設置させ着陸するのが特徴です。
カメラが載っているんですけれども、これで月のクレーターを撮影して瞬時に今月の上のどこにいるのかというのを割り出して次の目標地点に素早く修正して飛んでいくと、そういうようなことをSLIMが自身で考えてやるというのが非常に重要な技術でして、この部分には注目していただきたいなというふうに思います。
SLIMが月に着陸する際には降りてくる向きや角度にもよるんですが、最大で2トン近くの荷重がSLIMに加わります。加えられてもSLIM全体が壊れないような設計をするのが一番苦労した点です。
マルチバンド分光カメラなんですけれども、SLIMの本体と同様に小さなもので作らなきゃいけないですし、軽くなければいけないというたくさんの制約があったので、それを達成するために観測機器のチームでですね、すごく知恵を絞っていろいろな新しい技術を取り入れて挑戦的なカメラになっています。
SLIMが切り開くピンポイント着陸をはじめとする技術は今後どのような形で花開いていくのでしょうか。
ここでやられます技術は将来の月探査におきましても大変重要な技術様式であります。でこれをさらに応用いたしまして日本から続々と探査機を月表面に送り込みたいと考えております。具体的には月極域探査ルペックスローバーであるとか、宇宙飛行士を活動させるための有人与圧ローバーといったものが計画されております。月に進出するのみならず火星探査におきましてこの技術は応用される見込みになってございます。ここで新しい技術を獲得することによってますます日本は自由自在に宇宙で活動することができることになろうと考えているものです。これからも JAXA 宇宙科学研究所は挑戦をし続けます。
We will now discuss more about the moon landing with SLIM with our guests on this broadcast. Our first guest is from the SLIM project team, Mori Osamu, in the Department of Interdisciplinary Space Science here at ISIS JAXA. Mori-san is going to start by giving us an overview of the SLIM mission.
はい、それでは森さんには、SLIMの概要であるとか、それから打ち上げからここまでの経緯について、解説をしていただきたいと思います。よろしくお願いします。はい。
We're going to share some slides. Here we go. So, from an era of landing where we can, we're going to move with SLIM to an era of landing where we want. So the SLIM mission has two main objectives. Objective A is a technology demonstration of a high-precision pinpoint landing on the moon. With a soft landing by SLIM, Japan will be the fifth country to land on the moon after the Soviet Union, USA, China and India. But the landing precision will be the highest in the world. So conventional lunar landers actually have a landing accuracy of several to tens kilometers, whereas SLIM is aiming for a landing accuracy of only about 100 meters. And this technology is necessary for the era of full-scale lunar surface exploration activities where we want to control very precisely where we're going. The second objective, Objective B of the SLIM mission, is the realization of a lightweight lunar planetary probe system. So SLIM includes innovative weight reduction through improvements to the spacecraft structure, chemical propulsion system, power supply and orbit. And this will lead the development of a lightweight lunar probe will lead to the ability to have an increased payload for missions, such as, for example, sample return missions from the Earth or to Mars, or really anywhere else, because you have more of that weight available for instruments. So from here we're going to look a little bit more at SLIM's configuration and some of the components that allowed it to be such a lightweight spacecraft. So here we have the SLIM configuration itself. The mass of SLIM is 190 kilograms when it's in what we call a dry condition, that is, there's no fuel. And it's 710 kilograms when it's wet, so this is at launch when it's fully fueled. And you can see the features of SLIM's design in these images, such as, for example, the thin film solar cells that stretch across the body of SLIM, and the navigation cameras that, as we'll see a bit later, are a key component to SLIM's pinpoint landing mechanism. You can also spot the two main thrusters of the main engine and the smaller auxiliary thrusters, of which there's 12 around the outside, and SLIM's feet on the right here, which are the small shock-absorbing meshes. So here we have a bit more of SLIM's structural design. Top to bottom here in Japanese is written the PAF rings, which couple to the rocket. After that there's the tank, which is also used as a structural base of the spacecraft. Below that there's the deck panels with the landing sensors mounted on them. Below that again there's the RCS panel, which has the thrusters. Then we have the electrical equipment box and the instrument box with the scientific observation camera. So one of the innovative things here is actually SLIM's tank, because it's this integrated dual oxidizer tank that reduces weight, and then the cylindrical tank itself forms the structural base of the spacecraft, which also significantly contributes to an overall mass reduction of that spacecraft. Now the bottom part of the slide shows the attitude of SLIM during landing. From about 50 meters above the surface, SLIM will rotate to a vertical position and start to descend. But just before landing, SLIM will lean forward so that its lean forward so its rearmost leg touches the surface first. Then the spacecraft tips forward onto its front two legs before stabilizing into this horizontal position. And in the bottom right here, we have the mascot SLIM Moon, which you'll often see on our Twitter feed, SLIM_JAXA. And now we're going to turn to the design actually of the SLIM tank, the chemical propulsion system. Now, as I previously mentioned, this is integrated fuel and oxidizer tank, which is designed to reduce the spacecraft weight. If you look at that sketch in the top middle of the slide, you actually have the oxidizer in the blue part at the top. The propellant fuel is in the bottom, and there's helium gas in between. And a lightweight diaphragm separates out these sections, and this is newly developed. It's made of PTFE, which I believe stands for polytetrafluoroethylene, and it's part of the new development for SLIM. So the main engine is actually seen at the bottom left of the slide, and it uses a ceramic combustion chamber that was actually developed here in Japan. And it's designed to use an impressive combination of a wide thrust range and pulse operation. It's not been found anywhere else so far. The high performance also helps the overall mass reduction of the propulsion system. And then on the bottom right, we have the auxiliary thrusters, which have a thrust of about 20 newtons. This is a 12-unit configuration. And by making a different pattern of thrusters fire at different times, you actually control the spacecraft attitude, orbit maneuver, and precise landing. Now we're taking a look at the power supply of the spacecraft. So at the top here we have the solar batteries. These are thin-filmed triple-junction solar cell sheets. They're lightweight, they're flexible, and they're highly efficient on curved surfaces such as the SLIM tank. Below that we have the batteries, the lithium-ion battery. The outer casing is made of stainless steel. There's two sets of these cells that are bound by carbon fibre reinforced plastic CFRP plates, and these are designed to stand vibration and impacts during launch, as well as charging and discharging in a vacuum environment. And then right at the bottom we have the integrated power control unit. This handles functions like solar power generation, the power distribution, heater control, battery charge and discharge, and thruster valve operation. So this is actually SLIM's orbit, which performed what we actually call a swing-by orbit, which means it reached the moon. It launched in September, and we actually reached the moon as early as October, at the beginning of that month. But rather than stopping there, we actually swung outwards, and this is the idea behind the swing-by orbit, going to a rather staggering distance of about 1.38 million kilometers from the Earth, before turning back and returning to the to the moon, where we intercepted again and went into orbit on Christmas Day. There SLIM goes, oh, and there's the swing by. And then we started going back towards the moon on the 6th of November before going into lunar orbit. So the advantage of this swing-by orbit is rather counterintuitively, it saves a lot of fuel, because while it's a very long distance, when you reach these very far distances from the Earth and Moon, you can actually use the gravity of the Sun, Moon and Earth to bring you back towards the Moon without exerting a lot of thruster fuel. So it's long, but it's efficient. Now once we entered into orbit on Christmas Day, we started to change the orbit to become more circular. SLIM entered originally an elliptical orbit, and then passing between 4,000 kilometers and 600 kilometers from the lunar surface, and then it became more circular and has gradually been lowering since then. So let's look at the demonstration of the technology needed for high precision landing, this pinpoint landing on the moon. So how does SLIM actually do this very accurate landing? Oh, we've gone back to look at the spacecraft design again, and in particular these solar panels, which are flexible and fold around the fuel tank as opposed to being the flat wings that you normally see with conventional spacecraft. This is very efficient for space, among other things.
This is because SLIM will be landing in the morning, and it needs more sunlight, so it has to be tilted.
Okay, now we are going to go and look at the technology for the high precision landing, and in particular this pinpoint landing technique. This is the mission movie for SLIM. We're going to do a run through from the launch through to arriving at the moon. So this is a spacecraft separation. And then the first step is both an Earth swing-by, where we use the gravity of the Earth to give us a kick in the right direction. And this is followed by the lunar swing-by that we mentioned earlier, where we actually pass the moon and go out to a much further distance in order to use the gravity of the Earth-Moon-Sun system to pull us back. And now we're observations from lunar orbit. This is part of the vision-based navigation using the onboard cameras. So SLIM's cameras scan the ground beneath it on the lunar surface and identify craters, which helps SLIM know where it is. Now we rotate to a vertical position as we prepare for landing. And SLIM starts scanning the ground again, this time looking for obstacles that would actually be dangerous to the spacecraft should it land directly on them, for example, large boulders. And if it spots a large boulder, it moves horizontally in order to avoid that boulder and to an open space. And then just before landing, it's going to release the spacecraft's two rovers, LEV-1 and LEV-2. And then here is the two-step landing where we land on that back lead first and then tip forward onto the front landing gear. These are the two rovers, LEV-1 and LEV-2. And this is the movement of LEV-1, which is a hop. And this is LEV-2, the little ball rover. We'll talk a little more about that later. It springs open to actually have a wheeled format, so it will be moving along the lunar surface with wheels. And SLIM is also equipped with a near-infrared multi-band camera, and it will take observations from there. So now we look again at this landing sequence. So the spacecraft starts with a powered descent from an altitude of 15 kilometers and approaches the target point on the lunar surface using this image matching navigation, where it's spotting craters with its navigation camera and autonomously then guiding to its correct location. At an altitude of 7 kilometers, the spacecraft will transition to a vertical descent, and precise measurements of the altitude will be taken with the landing radar. And then finally, the two-step landing with the autonomous obstacle detection that we saw in the movie will be performed before we're safely on the ground. And the maximum, during the power descent phase, the maximum velocity is 1700 meters per second, and that is about 7 times the speed of a passenger aircraft. And this whole thing will take about 20 minutes, which is sometimes known by the team as 20 minutes of terror. So how do you actually know where you are on the lunar surface to do these pinpoint landings? Unfortunately, unlike the Earth, there is no GPS on the moon. GPS devices do not work. So therefore, we need to use other ways to find our location over the lunar surface. Now, conventional landers plot their trajectory from the Earth, and then they use their inertial navigation equipment, such as the accelerometers and the gyrosensors, to work out where they are. And then this allows them to find roughly their target location and land. However, those techniques are not particularly accurate, and little measurement errors add up all the way through to end up as a result with quite a large landing area with these conventional techniques. So in order to improve this, what we do is we add in this image matching scheme, which allows SLIM to have a much better assessment of where it is on that lunar surface by using its navigation cameras to photograph the pattern of craters below it on that lunar surface. So here's the process of that. We capture images with the navigation camera on SLIM, and then an extraction software program is performed to actually identify those craters, which are now circled in blue. And then with that pattern of craters, SLIM compares it with its onboard maps, which it's got from previous orbiter missions, such as Kaguya and from NASA's LRO orbiter. And that crater pattern can actually identify very accurately where it is on the surface. And so in addition to its inertial navigation equipment, it has a much better idea of its location, and then it can autonomously correct to find out where it is. Now in Hayabusa and Hayabusa 2, which were the asteroid explorers led by JAXA, actual people perform the image matching operation as opposed to inbuilt software. But SLIM has the issue that it's not landing on an asteroid, rather it's landing on a moon. And while the moon is much smaller than the Earth, its gravity is much greater than that of an asteroid, and you can't have a slow descent. So as a result, you actually need to do this image matching scheme incredibly fast, otherwise the lunar gravity has just pulled you past the point where it's useful. Now the other factor you've got to consider is that space computers only have about 1/100th of the capacity of their terrestrial counterparts due to the very harsh conditions of space. So as a result, the team had to develop this image matching algorithm that required only a few seconds of processor time, otherwise you'd miss your chance, on equipment that was not cutting edge. And there's no redo on a moon landing. Once you start that descent, that is it. You can't just pull up and start again, unlike on an asteroid. So now we have a look at a couple of the other navigation equipments on board SLIM. The top is the navigation camera. These are 2 units that are actually placed at different orientations so that SLIM can examine the surface both during the para descent phase and during the vertical descent phase when the spacecraft is tilted at a different angle. The middle part here is the landing radar. This is an altitude range sensor to measure the altitude and velocity in the direction of the lunar surface during that vertical descent phase. And finally, we have the laser rangefinder, which is much more accurate, and it's used during that final descent to pinpoint the altitude immediately before landing. So once we get to the point of the landing, we're actually landing on something that should be a 15-degree slope, and that's dangerous. It's very difficult to do. So in order to land safely on a fairly steep incline, we actually have this 2-step landing system was adopted. And this was developed after copious amounts of simulations, both computer and practical, to find out what's the safest combination for a spacecraft like SLIM so that it doesn't tip over. And the ultimate result was you land on the back legs and then you rock forward, as we saw in the movie, to a stable position. Now, the legs of SLIM themselves are actually these 3D printed semicircular aluminium spheres, and they're designed to compress to absorb the impact of SLIM landing on the surface. This is a very compact design because much larger missions would use legs with joints, but SLIM doesn't have the space for that, so they have these very compact, crunchable 3D aluminium spheres. Now, just before SLIM lands, it's going to release 2 lunar excursion vehicles, LEV-1 and LEV-2, and these will be a demonstration of small probe movement technology on the lunar surface environment. So LEV-1 is the bigger of the two, it's 2.1 kilograms, 26 by 40 by 30 centimeters, and LEV-2 is the smaller round ball at 0.25 kilograms. And these two will communicate as follows. The LEV-1 will actually talk directly to the Earth, and it will move through this hopping motion where there is an arm that presses forward onto the lunar surface and it causes the rover to jump. And it has an antenna, so it can communicate its pictures and other information back to the Earth. LEV-2 is smaller. It's going to have wheels because it springs apart from its spherical configuration into these 2-wheeled parts, and it will send its data via LEV-1 back to the Earth. This is a close-up of the movement of LEV-1. It has this punching arm that pushes down to the lunar surface. Because the moon gravity is very weak, this is actually very effective. And the rover should jump forward a fair distance before coming back down to the moon. And this is LEV-2, also known as SORA-Q, and it starts off in a ball configuration, but once it lands, it actually pops forward, and it has these 2 modes of motion, this kind of crawl, and also a more butterfly-like motion. And so here we are, designing technology from an era of landing where we can to landing where we want. And if you're feeling worried that you didn't manage to absorb everything that was said, Mori-san will be back to take us through the key points just before we begin descent. So our next guests are members of the private company manufacturing behind the SLIM mission. First we have Okaida Yu, who's from the Mitsubishi Electric Company, sometimes referred to as Melco, and these are the spacecraft system contractors. Okaida-san is based at Kamakura Works, where SLIM was constructed. So Mitsubishi had actually a very tough job, since as we've seen, SLIM needed to be made as lightweight as possible. So if the spacecraft can be made lightweight, like SLIM, then you do have the option of increasing the mass available for possible observation equipment, and also costs such as transportation to the rocket can be kept very low. Such development therefore can lead to more frequent lunar and planetary exploration in the future. So this is why a lightweight mission was very important for SLIM, and the challenge of construction was passed at least in part to Melco. So one example of that is that SLIM's tank was a new design because it acted as the body of the spacecraft as well as storing the fuel. This actually meant the tank was more exposed, and various devices had to be attached to the tank exterior. This was a new problem that had to be considered very carefully during the construction. Melco are also the spacecraft systems contractor for one of JAXA's upcoming missions, the Martian Moons Exploration Mission, MMX. MMX will launch in fiscal year 2026 and visit the moons of Mars, Phobos and Deimos. Spacecrafts will land on Phobos and collect a sample from the moon, returning to the Earth in 2031. So our next guest is Akagi Kensuke from Takura Tomy. Now, Takura Tomy is very well known, but not for spacecraft. It's most well known for being a Japanese toy maker company. The company is perhaps most famous for originally creating the Transformers, the alien robots that can disguise themselves as machines. However, in this case, Takura Tomy have built LEV-2, as seen here. It's a tiny little robot, also known as SORA-Q, and it's one of the rovers on the SLIM mission. And LEV 2 does indeed transform into the second image that you can see that Shin is holding. The rover is about the size of a baseball. It has a honeycomb aluminium alloy shell and starts off as a sphere, as you can see from Akaki-san's model that he's holding. And it then splits in half to reveal a pair of cameras that point front and back. And the two hemispheres actually become the rover wheels. So this little transforming robot will photograph the SLIM spacecraft and also the surrounding terrain before sending those images back via LEV 1 to the Earth. That's the front-forming cameras. And at the back it's even got a little tail for balance.
So the first part was from the toy of the transformer. So it's called a transformation technique that it has been developing. And the second one is this. So imagine that the sea turtles move on the shore, and they're inspired by the movements, and then they try to capture and then try to have that mechanism embedded.
So what I'm hearing is this is a transformer sea turtle.
Yes, that's right.
That's wonderful.
その思考の柔軟性っていったところですか、こういうものは空機レブ2の開発のどういった部分に生かされているみたいなのがあるでしょうか。
そうですね。やっぱりこの空機を作っていく中ではこのおもちゃの技術を入れていくとか、皆さんの周りも人大好きなおもちゃが月でも活躍するかもしれないなと思うと、こう普通の考え方というよりかですね、ちょっとこうぶっ飛んだ考え方。
It looks like this has been really creative process to invent this sort of toy, and is that right? And then he thinks that this is because of the company's strengths that the toy has been made into the space.
Excellent. And toys like Transformers are incredibly imaginative, so maybe this is a more logical step than we might have previously considered.
And it is unique.
It is unique.
はい、続いてのゲストをご紹介しましょう。はい、どうぞ。
So our next guest is Murata Tomakatsu from the Graduate School of Science in the University of Tokyo.
研究家の諸田智勝さんです。よろしくお願いします。
よろしくお願いします。
So Murata-san is particularly interested in the science rather than engineering behind SLIM and the science SLIM plans to do on the lunar surface. Murata-san has previously worked with a lot of lunar observation data, including that from the JAXA lunar orbiter Kaguya. So Kaguya, which was launched in 2007, orbited the moon and mapped the moon's geology all over its surface. The result were these very high-resolution maps that Kaguya and similar missions, such as NASA's Lunar Reconnaissance Orbiter, LRO, revealed. And you see these key bodies of rock that aren't particularly large areas, but are really interesting, and they could shed some light onto important questions in planetary science, such as those related to the moon's formation. So you have this situation now where you have fairly small but numerous regions of interest that you really want to get a look at. And this brings us to the need for SLIM's pinpoint landing technology and the ability to land on slopes, which enables us to choose a much wider region of possible landing sites and also land on some rough terrain, which is what we're seeing here. And we can actually get close enough with this technology to actually start studying these areas. So this important use case means that while SLIM is a technology mission and it's designed to be testing the pinpoint landing technology on slope terrain, the spacecraft is also equipped with a scientific instrument, the near-infrared multi-band camera, and it's designed to investigate the composition of the surrounding rocks after landing. And this takes us on to considering the landing destination for SLIM, which is near the Scioli crater, which I hope I'm pronouncing correctly. So Scioli is an impact crater, meaning that it was formed when a meteorite struck the moon's surface. When a crater forms through an impact event, the debris from the deep interior can be ejected, and a central hill forms from those exposed deep materials. So in and around impact craters, we expect to possibly find rocks from the moon's deep interior that have been ejected. and these are often found in mounds in the center of craters or the surrounding boulders in that region. So one of the minerals that is particularly interesting for this is olivine, which is quite a heavy mineral, and we expect it to have sunk into the moon's mantle during its formation. Therefore, if we spot olivine on the surface, it's probably a mantle rock that's been ejected from the moon's interior. And if we could land near one of those olivine-containing rocks and compare their composition with those on the Earth, it can tell us more about how the moon formed.
And it might be taking like an hour to explain, but he'll try to say it in 1 minute.
So here's a moon, and this is the
So this is the shape of the rabbit, and you can see. And this is a pattern that you can recognize on the moon.
So in Japan, well, the rabbit is what's seen on the moon's surface.
That's right. And here he's pointing out the finger, and in that area.
This is Mare Nectaris.
Yeah. So the Shiori crater is just right there at the spot of the right ear of the rabbit. And then it's trying to land on this exact spot, as you explained. So here it is. This is the rabbit's ear, and there are two rabbit ears. And the bottom one is the western side, and then this is where the crater is.
So this is the landing site for SLIM. It's going to be on this crater where we think we're going to have exposed olivine material from the moon's mantle. And it's on this sloped terrain, so we have to land very accurately and on a slope.
The crater itself is very small, like 1 kilometer, but SLIM is trying to get that. So by going there, by SLIM, what will we be able to find out? So this is beyond the SLIM's scope, but could you please tell us about the importance of this research?
So one of the main theories for the moon's formation is that it formed during a giant impact with the Earth. If that's true, the composition of the moon's mantle, which is about 90% of the moon, would be expected to be similar to the Earth. So if we can identify a mantle rock, i.e. that olivine, and look at its composition in more detail, we'll learn more about the moon's formation. So Kaguya examined the moon's geology all over its surface. It spotted that near the Shiori crater was a place where the mantle rock seems to become exposed. And that's why SLIM is planning to touch down in this very small area and examine it with its multi-band camera.
Could you please tell us more about this crater, Shiori?
こちらにあります。この幹の海の西側にはそのシオリクレーターという月のおそらくマントルですね、地下の物質が天体衝突によって掘り返されて今表面に露出している。
So at the bottom of the slide here, we're actually seeing a model for how the moon might have formed. If we look at these cuts, they're actually cuts through a would-be moon. These sort of pizza slices where the core is at the bottom, and then the surface is at the top. So going from left to right, the first slice, the green circles are this olivine, which is floating in initially a molten magma ocean. It is thought to have existed on the moon when it first formed. If we go towards the right, we're going to see the moon start to evolve. This is the evolution a little later. The relatively heavy olivine has now sunk down to become sediment and begins to form the mantle. In slice 3, the lighter, buoyant, calcium-rich plagioclase crystals, which were actually shown by little rectangles at the top, were rising to the surface, and these form the moon's crust. So then we only see olivine again if you can dig up some of that mantle, for example, during a meteorite impact, which might have created the Shiori crater.
So in the larger picture, that the scientists will be comparing the formation of the moon and the formation of the Earth.
By looking at that composition of the olivine, which should have come from the moon's mantle.
地球に何か天体がぶつかって、それで月ができたっていうジャイアントインパクト説なのか、それともなんか別の方法でできたのかっていうことが、その結論までもしかしたらできるかもしれない。はい、そういう議論までいけるかもしれない。
The question is if that was a giant impact that created the Earth or not, but there might be more theory to come. So the research will be developed from this point onward.
画期的なやっぱり技術になるということで、これからの月探査のやっぱりここにしおりを入れるイメージでつけられたと聞いております。はい。
So Shiori has a double meaning that by doing this, landing on this crater, it will leave the mark on history. And Shiori in Japanese means marking. So this is a double meaning.
Oh, that's lovely.
Okay, our last guest is JAXA's Vice President, Sasaki Hiroshi.
佐々木宏さんです。よろしくお願いいたします。よろしくお願いします。佐々木さんは日本のアルテミス計画を統括されていると。
So VP Sasaki is the Director General for Human Spaceflight Technology Directorate and the leader for Japan's participation in Artemis. So could you please tell us about what you are doing right now for the Artemis?
日本が参画をするというふうに発表しています。その際に参画としては大きく3つ。
So Japan has already said that it will be participating in Artemis. And then there are 3 things that we will be planning on doing.
それを今後のアルテミス計画に参考にするといったものが1つ。それから月の有人の周回拠点ゲートウェイ、これに対して生命維持装置を提供するとか物資を補給するといったものがもう1つ。それから最後が有人油圧ローバーを開発。この3つになります。
Okay, so the main goal of the Artemis program is to establish a human presence on the moon, but while doing so, that Japan will be contributing more on the robotics as well. And the first one is the crewed mission that will be setting on the foot on the lunar surface, and also another one will be sending the pressurized rover for crew driving on the lunar surface. So in Washington, D.C. as well, that he has just been to, that they are paying much attention to this project SLIM. And because this is leading more techniques to be developed for Artemis in the future, so it has like a lot of anticipation and also excitement. And for Artemis project to be going on, that the both sides, so crewed and then uncrewed, so manned and unmanned projects are important. So they have to be developed in tandem. So the SLIM will just go on and then first focusing on the technology and what more can you do with this technique? So this SLIM's technique will leading us to go to the narrow space or the hidden space. So it will give us much freedom to move around on the Mars surface, on the moon surface. And then there will be more applications in the future. So we will be having more presence and also we will be building more trust with the partners. And it has been that Japan has great trust building by presenting trustful rockets. And also, we are adding more to this trust in the international partners, so that this technique will be highlighted and then it will be developed more in the near future. So what's next? And then what can we say about the projects coming after SLIM?
今後のミッション、複数いろいろと検討していて、今後このスリムが成功した暁にはどんどん次に進んでいく。
So we already have few more things planned in the future. So this will be the critical time for us to look at the success of the SLIM.
こういったものが、そうですね、佐々木さんが統括されているところで、今後進めていくということなんですね。
So does it include the pressurized rover? And yes. The rover as well, that it will go to the place where they want to go. So the pinpoint landing is necessary.
そういうところでこういう無人探査でしっかりとこう行くということが大事で。
But the rovers can only go to the safer places. So building this technique and then going to the place where it's sort of hidden or it's very difficult to go, and it's still the technology will be useful in the future.
人が行くのは難しいっていうところはやっぱりその無人探査がまだまだその技術を持って実証していく、実際に実現していくっていうところ。
So that's exactly why VP Sasaki has been emphasizing the importance of both manned and unmanned exploration. And thank you very much.
はい、ここでですね、いろいろ質問が来ておりまして。
So now we're going to return to Mori-san, who's going to remind us of the key points as we head towards descent and landing. So here's our summary slide of SLIM attempting a pinpoint landing on the moon. The powered descent is from an altitude of 15 kilometers with 3 thruster boosts and coasting in between. We approach the target site on the lunar surface using this image matching navigation technology, where we're going to match the craters to known patterns on our onboard map using the navigation camera and autonomous guiding control. Then we begin the vertical descent from a 7-kilometer altitude. This includes 3 short hovering times. And we also do obstacle detection to avoid any dangerous boulders from about a 50-meter altitude. And then the 2 little LEV rovers are released at a 2-meter altitude before we do the 2-step landing on the sloped terrain. And we're aiming for a lunar landing accuracy of order 100 meters during this 20 minutes of terror. Landing can be confirmed relatively quickly, but more than that to do with the pinpoint landing accuracy might be determined as much as a month from landing.
This curve is very important because we start from the altitude 15 kilometers, and by pushing it forward from that point, it will be going a little bit upwards, and then that will be very useful for the landing technique going vertical. And also the engine will be shooting down, so that energy will put the probe up there. So this curve itself is very much suitable for pinpoint landing.
今回非常に攻めた設計に見えるけど確立された手法なのでしょうかという質問が来ています。
So this looks like a very difficult design, but what kind of things did you do to make it possible? Because SLIM looks like, very much challenging, including many new techniques. So could you please tell us about the highlights? So that's right, that there are many techniques that they are pushing, and also they are really new and innovative. So what the team tried to do the most is try to have more and more experiments, and by getting successes, they are very confident to place those techniques put together in this probe SLIM. The rocket launched on the 7th of September, and around 4 months later that we are here today. And other missions, such as Russians and Indians, they took less time. So why did SLIM take 4 months? Could you please explain to us about it?
軌道ですね。早く入っていくこともできるんですけど、途中の軌道で少しお示ししましたように、最初月に入った後にそのまま月周回に投入に月周回軌道に投入することもできるんですけど、それやってしまうと燃料をかなり使ってしまいます。
So this is something that we saw on the slide. So the swing by, we could probably just do one swing by to get into the moon's orbit, but by doing so, we need to put so much fuel on the probe. But we want to have less in a tank, so we decided to do the longer swing by and then have this SLIM orbit. So we chose this to have more efficient, and this has become one of the main goal of the SLIM project.
So it's somewhat counterintuitive that this very long swing-by orbit turns out to be much more efficient on fuel. But even though it takes longer and it goes further, it is able to use the gravity of this Sun-Earth-Moon system to actually alter the position and attitude of the spacecraft, to put it back onto a trajectory towards the Moon. And this is actually much cheaper on fuel as opposed to braking when you reach the Moon the first time, to enter lunar orbit straight away.
That's right.
はい、そうですね。成功するためにやってきた。
So what do you think that will be successful?
もちろんこれまでの実績で言うと、いろんな海外でもいろいろ苦労しながら、失敗も重ねながらやってきているっていうのは。
And it has been like many challenges and also failures, as we all know, but we would like to believe that this will work today. And we have many experiments and then many discussions. So today we believe that things will work. And sorry for asking the difficult questions, but as Mori-san explained, that many experiments proved that this technique should work. So, okay, next question, or maybe comments from the audience.
As an aside, if you look at the Moon that's in front of it's just gone off camera, but to the left of that is one of the actual landing legs from SLIM, so you can examine its mesh crushable structure when it comes back on camera.
So, can anyone observe it through the observatories or the telescope? And Mori-san's answer is that it's probably very difficult.
We can't see SLIM.
Too bad. So could you also tell us about this plan of landing on the slope? So could you please explain to me a little bit more?
So from this angle you can see the 5 legs on the SLIM spacecraft, the rear leg that sticks out the furthest, and then a more square structure for the forward landing gear and middle landing gear. So SLIM initially descends vertically and it's going to land on that rearmost leg first. That's the first one that's going to touch the lunar surface. So it lands on the back leg and then it tips forward onto those front 2 legs.
2 steps.
着陸するというわけですね。ちなみにですね、ちょっと気になるものが横にあるんですけれども、これが着陸の
Let us see this model. What is it?
衝撃を吸収するものとなっていまして、
I'm glad they came back to this.
これが実際に足についているわけです。
そうですね。この
Yeah, it's one of these little legs. So while a big lunar lander, such as Apollo, actually has legs with a joint that are able to absorb the impact, SLIM has these very compact lattice-like legs that will compress on impact and absorb that force as it comes down on the lunar surface.
ここまで質問とコメントの紹介をさせていただきました。さてですね、着陸に向けた
So this is the end of the Q&A and comment
となりまし
section.
た。ここで改めて、森さんに、スリムのポイントとそれから着陸
So there are only 5 minutes to go. So Mori-san will review what will be happening in the next in the next few minutes.
So this is our pinpoint landing again, the powered descent from 15 kilometers, the vertical descent from 7 kilometers, the search for possible hazards, such as boulders.
So overall, when it starts, it will take about 20 minutes.
20 minutes of terror.
So first it approaches to the targeted position, and then the vertical descent. And it will have 3 hoverings, and it will try to detect any boulders. And then it approaches to the slope and have 2-step descent and landing.
短時間で確認できますが、このピンポイント着陸の成否は着陸後1ヶ月以内を見込んでいると。
So it will be determined relatively soon about the landing itself, but the pinpoint or not, so how precise it was, it will take about a month to process.
テレメトリーというのは、その探査機からスリムから送られてくるさまざまなデータのことを表す言葉です。
So now let us explain about the telemetry. So we will be moving forward to the screen like this, and the telemetry is the data that has been sent from the probe.
So this is the QL quick look screen, and we'll see this during the descent to the lunar surface, and it will display the telemetry, the data coming from the spacecraft. And we're going to go through just each of what you're seeing here to explain what it means. So this is the date and the time, in the top yellow. It's a spacecraft time, but that corresponds almost exactly with Earth time, as it only takes about a second for radio waves to travel between the Moon and the Earth. It's showing the time in UTC, Universal Time, which is Japan time at -9 hours. Now this part is the GNC Guidance Navigation Control mode, and you can see the different options for the modes, with SPM being sun pointing mode, OCM being orbital control mode, etc. And it tells you what phase we're in at the moment. This is going to show us the spacecraft acceleration. It's the actual measured value of the accelerometer is on the left. The estimated value based on the model is on the right, and descending order for the acceleration goes from green through to red. This shows the status of the auxiliary thrusters. The scale here goes from 0 to 100%. And this is the status of the main engine injection, with the scale again going from 0 through to 100%. This shows the angular velocity of the spacecraft along the 3 axes, X, Y, and Z. The colours here indicate descending orders of control error, with green having minimal control error. Gosh, we're going faster. This is the remaining propellant. The fuel is on the left, the oxidizer is in the middle, the total is on the right. The fuel to oxidizer ratio is 1 to 0.8. The BAT SOC is the remaining battery capacity, and now we are looking at, if this graph looks like this, it's the mode before powered descent. So altitude from the sun is seen on the left, the altitude from the Earth is on the right. This is now what it looks like when we go into the powered descent mode, showing positional information such as the trajectory, white line, and the actual trajectory. Is that right in the red line? No, this is the vertical descent mode. My apologies. The last one was the powered descent mode. This is vertical descent mode. And so that takes us into an era of landing where we can to landing where we want.
So on the screen, you will see the same telemetry as the mission control room will be seeing. So we are now switching the screen to the telemetry.
ここからは、森さんと私で、テレメトリの画面を見ながら進めてまいりたいと思います。
はい、今
So during this phase, as we head towards the lunar surface, we are not going to say a great deal. Please watch the telemetry, and so you can see for yourself how the spacecraft is progressing, and there will be minimal commentary during this time.
で、メインエンジンが今 100% になってますね。これもブーストをしている状態ですね。完全に噴射していて、今ブレーキをかけている状態と言っていいかと思います。
Main engine is 100%. That means that it put the brakes. And now the altitude is 15 kilometers and slightly up.
白い軌道、右側のグラフのところで白いラインが目標となる軌道になっていて、
So on the right, you see the graph, and the white is expected orbit. And the red one is how SLIM is going.
それなりに合っていれば、大体目標通りの軌道で飛んでいるということがわかるかと思います。
So now SLIM is going more or less on the planned trajectory.
先ほど、動力降下シーケンスが開始されています。午前0時頃から、動力降下シーケンスが開始されておりまして、
And it started descent.
ブーストが行われております。
これしばらくブーストが続いて、そのうちしばらく時間が経つと1回休憩になります。コースティングモード、コースティングに入ります。
はい、コースティングというのは完成工法。
そうですね。特にエンジンを吹かずに、補助エンジンは補助
So now the engines are on, but soon it will be turned off, just for a while.
静かに飛んでいる状態。
And then it will fly a little bit without thrashing.
表示している画面、右下には第二管制室の様子を示しています。
And on the right-hand corner, you see the second control room.
こちらも画面に表示されているのは今この YouTube の画面に表示されている、テレメトリ表示画面と同じようなものを
And in the second control room as well, that they are seeing the same exact telemetry as we see here on the screen.
真ん中の画面がそうですね。実際今先ほどの画面と同じ画面になってますね。今メインエンジンは2個 100% 噴射してますが、補助スラスターは12個ありますが、噴射しているものと噴射しないものがあって、これは軌道とか姿勢を補正したりするのに使われてますので、噴射の仕方はいろいろ変わってくるといったものになります。
はい、現在、第1回目のブーストを実施中です。高度はそうですね、20キロを上回ってきたあたりになるかと思います。
The altitude is now 20 kilometers, and this is the phase of the first boost, and it will keep going for a while.
これはメインエンジンがずっと噴射しているので、どんどん水薬が使われているっていうことを意味しています。
はい、画面の右上ですね、青色が
そうですね。FU って書いてあるのが燃料。で、OX って書いてあるのが酸化剤ですね。
Fuel, and you can see it on the right top corners, and it will have to decrease as it goes.
画面では、現在第1回の燃焼を実施中です。
で、左下の、加速度計の表示が、あります。A って書いてあるのが加速度計で、B がモデルで計算した数字なんです。大体一致していて、緑なので十分加速度が出ているってことを表しています。
The velocity is just about right, so you can see it on the left bottom, and now you can see both A and B are green, and it has been as it has been planned, so things are going okay on that side as well.
はい、間もなく高度が25キロのあたりに到達するかと思います。
そろそろ、コースティングに入るかなと思います。
The altitude is now reaching 25 kilometers, and it will now go into coasting mode.
いう状態です。で、この間に、先ほどの 画像照合工法を行います。で、位置を、今まで蓄積した誤差を一回これでリセットできる、位置がバチンと決まりますので、これで、完成工法でやってた位置のズレをこれでリセットするといった操作が行われます。
はい。現在、SLIM は画像照合工法を実施中と思われます。
So now it started to scan on the moon's surface. So it's looking for the exact place to land.
はい。高度は25キロ上回ったあたりです。
The altitude is just about 25 kilometers.
はい。今、メインエンジン着火しましたね。100% になりました。これで第2回のブーストが始まりました。またこれでしばらくずっと噴射状態が続くかと思います。
はい、時刻は0時5分を、0時6分ぐらいです。現在、SLIM は第2回のブーストを開始しています。
So SLIM is going into the second phase of boost. So now you can see the engine firing.
緑色に表示されているかと思いますが、これ緑色になっているってことは、姿勢が姿勢の制御が想定通りになっていると、姿勢誤差が小さいということを表しています。赤い軌道も、赤のラインも白のラインと大体一致しているので、基準軌道に沿って進んでいるというふうに考えていいかと思います。
Now you can see the planned trajectory, and the red trajectory is going on the model. So this is going very close to the planned trajectory.
はい、少しずつ高度が下がってきています、ね。
そうですね。だいぶブレーキが効いてきましたね。最初軌道が先ほどお話した理由で上がってたんですが、はい、もう落ちてきましたね。
It start to descend a little bit, as you can see on the right side. It's still doing the second boost.
ブーストを実施中です。
燃料酸化剤もだいぶ減ってきましたね。100キロもう割り込んできました。これ着陸しても全部途中でなくなるっていうわけではなくて、少し残るような、10キロ以上は残るような計算になっています。
Fuel is also decreasing, as you can see on the right top corner. And now you can see 96.6 kilograms of fuel, and it will be about 10 kilograms or even a little bit slightly more. So that's where we are aiming at. So it will not be completely empty.
緑のバーが今出てますが、最初2ぐらいだったのは今少し高くなってきていると思いますが、これ同じ水力は同じなんで、探査機の質量が小さくなったので加速度が増えているっていうふうに見ていいかと思います。
Velocity is increasing. That's on the left-hand side, and because the mass is decreasing, that means velocity is getting a little bit more in number.
第2回のブーストを実施中です。動力降下シーケンスにおいて第2回のブーストを実施中です。
もうしばらく続きそうですね。はい。
It will continue a little bit. We are still on the second boost stage.
は
はい、スリムは、現在第2回のブーストを実施中です。スリムは第2回のブーストを実施中です。高度がかなり下がってきましたね。
そうですね。もうちょっといくと思いますね、このまま。はい。
はい。
15キロ下回るぐらいまでは、このまま 100% のブーストでいくと思います。で、12個の
Now install the second boost stage, and it's now above 15 kilometer, and it will continue a little bit longer.
はい、スリムは、高度20キロほどに到達しています。現在、第2回のブーストを実施中ですが、高度が20キロほどまで降りてきました。
姿勢もそうですね。今、オメガ X、オメガ Y、オメガ Z、すべて緑になっています。加速度も、緑できちんと老けているといったふうに見ていいかと思います。燃料酸化剤がだいぶ減ってきましたね。
はい、スリムは現在第2回の、ブーストを実施中です。スリムは第2回のブーストを実施中です。
Still the second boost.
15キロ割ってくると、再び、コースティングに入ると思います。また画像照合工法ですね、を実施するために、1回停止ということで、コースティングになるという見込みです。
So when it goes below altitude 15 kilometer, it will start the coasting again and then try to do the image scanning.
今、メインエンジン 0% になりましたので、これで第2回のブーストが終了して、コースティングに入りました。
Now you can see the engine has stopped like 0%. So now it starts cruising and trying to see the surface. So image scanning right now as it plans.
また第3回のブーストが始まるかと思います。
And soon we'll probably see the third phase of boost.
スリムは現在画像照合方法を行っている頃かと思われます。高度は10キロを下回ってまいりました。
そうですね。メインエンジンまた噴射しましたね。100% になりましたので、これで第3回のブーストが始まりました。
Now you see the engine is on now, 100%, and now the third stage of boost has just started. And the third one will not be 100% all the time. It's called the pulse thruster. So it's been expected that it's not going to be always 100% on.
これをしばらくまた続けまして、高度が適切な、十分落ちてきたところで垂直降下モードに切り替わります。今、左上で PDM と書いてあるところが、VDM という文字に切り替わると思います。
Now please pay attention to the left top. It's PDM. It will soon change.
第3回のブーストを行っているところです。スリムは第3回のブーストを行っているところです。
Into VDM. So PDM will change into VDM.
はい、高度がだいぶ下がってまいりました。10キロ下回って間もなく5キロに到達するかと思われるところです。
これで画面左側の今のグラフもこれで垂直降下モードに変わると、この今のグラフも切り替わります。
Now approaching altitude 5 kilometer.
はい、スリムは現在第3回のブーストを実施中です。スリムは第3回のブーストを実施中です。
そうですね。今 VDM という文字が左側に、緑の文字に変わったと思いますが。
Now it's been changed VDM. Now starting the vertical descent.
2つの探査機が乗ってる。これ、X 方向から見たのと Y 方向から見た、なんですか、図になっています。で、X 方向というのは、西方向。で、Y 方向、プラス Y が南の方向。
So X-axis is the west and the Y is south. Now,
16分30秒あたりですが、すでにスリムは垂直降下モードに入っています。
it started vertical descent.
垂直降下モードを実施中です。3000メートル割ってきました。
はい。で、これもしばらくパルスーン車ですね。今数字が 100%、メインエンジンのパーセンテージが 100% になったり、またそれ以外の数字になったりと切り替わってますが、これ、パルスーン車をしているので、こういった形で、変化していると言ってみていいかと思います。で、これで500メーターぐらいのところまでこのまま降りていきます。で、500メーターのところで1回目のホバリングに入ります。
It will descend around 500 meter and it will start the first hovering.
高度を下げております。スリムは垂直降下モードにて高度を下げております。1000メートル割り込みました。
そうですね。そろそろこれで500メートルなんで、ここで1回目のホバリングに入ると思います。しばらく高さを維持する状態になるかと思います。
Around 500 meter, it will start doing the first hovering.
高さが今一定になっているかと思います。はい、これホバリング状態。これそんなに長く続かないです。またすぐに降りていきます。
It will be a short time, but this is the first hovering.
第1回のホバリングを行って終えたと思われます。
再びそうですね、下がり始めましたね。高度が下がり始めました。
It starts to descend again, and next aim is 50 meters.
50メートルのところでは、先ほど少し紹介しました、障害物検知を行います。それで安全な場所を見つけて水平移動して、それも自立で安全な場所に移動すると、水平移動するといったことを行います。これも比較的短い時間で行う予定です。
So at the next point, it will scan again to see if there are any obstacles or boulders.
はい、高度が100メートルを下回りました。まもなく50メートルに到達しようというところです。
そうかな。はい、ここで一旦、はい、ホバリングに入った、2回目のホバリングに入った。
This is the second hovering.
これで安全な場所に水平移動を行って、その後またしばらく降下するという状態になります。
Now it's looking for the safe place to land.
を行っていると思われます。スリムは第2回のホバリングを行っていると思われます。障害物回避に
今降りましたね。はい、これで高度2メーターぐらいのところで第3回のホバリングを実施し、これでレブですね、超小型ローバーを放出します。でその後一気に降りて2段階着陸をするという形になるかと思います。
Around the 2 meters, it will release the lev and it will land. Two-step landing is expected.
モードが今 MLM というモードに切り替わりましたので、これで着陸したという状態になります。
Now you see on the left-hand side MLM. That means it has landed. From the telemetry, it shows the sign MLM.
判断が難しいところですけど、姿勢も少し傾いているように見えます。で、MLM というモードで、傾いて倒れていると、着陸したといったような状況に見えます。
はい、テレメトリーの表示画面の上では、スリムは月表面に、到達したかと思われます。高度は、月表面に到達したかと思われます。
From the telemetry, what we see is the SLIM has landed on the slope.
はい、テレメトリの画面上では、SLIM は、月の表面に、到達したかと思われます。テレメトリの画面の上では、SLIM は、月の表面に到達したかと思われます。はい、繰り返しお知らせします。SLIM は、テレメトリの表示画面の上では月の表面に、到達したかと思われます。SLIM は、月の表面に到達したかと思われます。
It looks like on the telemetry that SLIM is on the surface of the moon.
一連の動きはだいたい想定の通りの挙動を示していたように思います。
はい、現在 SLIM の状況を確認しています。SLIM の状況を現在確認中です。
We are now checking the status.
はい、画面の上では、SLIM は月の表面に、到達したと思われますが、現在、状況を確認しております。SLIM は、画面の上では、月の表面に到達したと思われますが、現在状況を確認しております。
From the screen, the SLIM is on the moon. We are checking the status right now.
はい、画面の上では、SLIM は月の表面に到達したと思われますが、現在 SLIM の状況を確認しています。画面の上では SLIM は月の表面に到達したと、思われますが、現在 SLIM の状況を確認しています。
We are now checking the status of the SLIM. It looks like it has reached on the moon from the screen that we see, but we are checking the status.
はい、画面の上では、SLIM は月の表面に到達したと思われますが、現在 SLIM の状況を確認しています。画面の上では SLIM は月の表面に到達したと思われますが、現在 SLIM の状況を確認しております。
We are still checking the status.
はい、画面の上では、SLIM は月の表面に到達したと思われますが、現在 SLIM の状況を確認中です。現在、SLIM の状況の確認中です。
We are still checking the status.
はい、現在 SLIM の状況を確認中です。現在 SLIM の状況を確認中です。はい、現在 SLIM の状況を確認中です。現在 SLIM の状況を確認中です。 はい、現在スリムの状況を確認しておりますので、もうしばらくお待ちください。現在スリムの状況を確認しておりますので、もうしばらくお待ちください。
We are still checking the status, so please wait. We are still checking the status, so please wait.
はい、現在スリムの状況を確認しておりますので、もうしばらくお待ちください。現在、スリムの状況を確認しておりますので、もうしばらくお待ちください。はい、スリムの状況確認のため、0時30分で番組を中断いたします。スリムの状況確認のため、0時30分で番組を中断いたします。なお、後ほど、ただいまご覧いただいております YouTube ライブにて、記者会見を中継いたしますので、開始までしばらくお待ちください。繰り返しお伝えします。スリムの状況確認のため、0時30分で番組を中断いたします。スリムの状況確認のため、0時30分で番組を中断いたします。なお、後ほど、ただいまご覧いただいております YouTube ライブにて、記者会見を中継いたしますので、開始までしばらくお待ちください。
So we are still checking the status. So we closed this session at 12:30, and later on the same link and the same website, that press conference will start. So please come back to the press conference. We are still checking the status.
スリムの状況確認のため、0時30分で番組を中断いたします。なお、後ほど、ただいまご覧いただいております YouTube ライブにて、記者会見を中継いたしますので、開始までしばらくお待ちください。
We are ending this program at 12:30, but we are still checking the status. Later on this channel, we will have the press conference. So please wait. We are still checking the status, and the press conference will start shortly. Thank you.
はい、スリムの状況確認のため、0時30分で番組を中断いたします。スリムの状況確認のため、0時30分で番組を中断いたします。なお、後ほど、ただいまご覧いただいております YouTube ライブにて、記者会見を中継いたしますので、開始までしばらくお待ちください。はい、スリムの状況確認のため、0時30分で番組を中断いたします。
So we will end this program at 12:30. The press conference will be held on the same link. So please wait until the press conference begins. We will be ending this program at 12:30. Thank you.
はい、こちらで、一旦、0時30分になりましたので、番組を中断いたします。ここまで、ご覧いただきありがとうございました。
For watching.
Thank you very much for staying with us.